Well, good morning. This is Wednesday, June 10th. I'm teaching lesson 6.1. What's in this lesson will not be on the Unit 5 test. There's actually two handouts you need for this. You need go to topic 6, topic Unit 6, go to the blank lesson for 6.01, but also open the blank lesson for, it says 10 connections, and those are 10 connections between limits and graphs. So we're going to put the G in vegans around. In fact, that's our first objective is 10 connections between limits and graphs. Then we're going to look at the graphs of the trig functions, linear transformations of parent and child functions, and we'll do some limit questions today. But first, let's go to 10 connections between limits and graphs. If you don't have that right in front of you, I'm going to go fast through this lesson. So be ready to pause for anything you need to digest. Pause, because I'm going to be talking really fast. So here we go. In the 10 connections between limits and graphs, we need to learn the definition of a removable versus a non-removable discontinuity. And there's, from the Larson text, there is a definition of a removable discontinuity here. But let's just talk about discontinuities in graphs. Discontinuities are essentially breaks in graphs. You can have a hole. In fact, just for concept development, a hole in the graph sometimes happens. Sometimes you get a jump in the graph. We call that a jump. And sometimes you get an asymptote in a graph, like let's say in the axes are in green. Suppose you have a vertical asymptote. So that's an odd vertical asymptote. You also have even vertical asymptotes. So there's three types of discontinuities: a hole, a jump, or a vertical asymptote. Okay, now of these asymptotes, a removable discontinuity, if you read the definition there in the text, it essentially shows you that the only type of removable discontinuity is a hole, because you can remove the continuity, you can remove the discontinuity by either defining f of c or redefining f of c. It's like, well, right now f of c is undefined, and suppose on the y-axis this is at c comma 8. Well, if we just say we're going to define f of c as 8, that removes the discontinuity. So a hole is a removable discontinuity. There's no way, suppose this is the point 5 comma 3 and this is the point 5 comma 7. There's no way to redefine f of 5. F of 5 is 3. If you redefine it and say f of 5 is 7, you still have a jump. That doesn't fix it. It's non-removable. There's no way you can redefine, suppose this is x equals 3. You can't redefine f of 3 to make the discontinuity go away. So the only type of discontinuity that is removable is a hole. A jump is a non-removable discontinuity, and asymptote is a non-removable discontinuity. So that's what that was all about. But the 10 connections between limits and graphs, most of those connections are down here in template form. So in the work that we've done with limits, we're going to take it the next step. Instead of just saying the limit is 8 or the limit is 12, we're going to say the limit is blank and the graph has blank. So it might be the limit is 12 or it could be the limit does not exist and the graph has an odd vertical asymptote at x equals a. The limit is whatever and the graph has this. These are the 10 most common ways to connect the limit to the graph. Let's practice on the next page, which for you looks like this. You have a graph. I hope you can see it. It should look like there's a branch here and a branch there, and this is, that's a little bit light. I believe this is the x-axis, and this is the horizontal line, y equals 2. And this is the vertical, not horizontal line. This is the horizontal asymptote at y equals 2. And I believe this is a vertical asymptote at x equals, I believe it's -4. It's at -4. So go ahead and make it dark enough for you to see that this is a two-branch graph. It's called a hyperbola. There's a horizontal asymptote at y equals 2 and a vertical asymptote at x equals -4. And the same graph keeps showing up problem after problem. So, based on the graph, we can say the limit as x approaches infinity of f of x is 2. But we need a statement. The statement that shows the connection between 2 and the graph. So the statement is, and you're going to have to write out the words. It's verbal. You're going to have to say, the limit is 2, and the graph, it's got to be and the graph has. Don't say and it has, say and the graph has a HA, I'll let you use that acronym, a horizontal asymptote at y equals 2. See, the limit of 2 is connected to some feature of the graph. It's the number in the equation of the horizontal asymptote. So there's a connection between the limit and the horizontal asymptote y equals 2. Whereas in problem 2, what's the limit as x approaches -4? Well, -4 from the left is infinity. -4 from the right is -infinity. So we say the limit does not exist. The connection statement is the limit does not exist, and the graph has an odd VA, vertical asymptote, at x equals -4. So the limit as x approaches -4 does not exist. There's a connection between this limit and some feature of the graph. This time it's not the horizontal asymptote at y equals 2. This time the connection is with the odd vertical asymptotes. Odd vertical asymptotes come up to the asymptote like this or that. Even vertical asymptotes come up like this or like that. You probably remember that from college algebra. Now, I'm going to ask you to try some of these on your own, and if you get stuck, just look at the bottom half of page 1 to help jog your memory or give you an idea of what the answer might be. So, if you're not sure what to do, look down here at the bottom of page 1. All right, so try this one on your own. It's the same graph, x-axis, y-axis, horizontal asymptote y equals 2, vertical asymptote x equals -4. Find the limit as x approaches 0, and then write a statement that explains the connection between your limit and this graph. So pause, try it on your own, and then we'll go over it. All right, so for these, actually, if all you do is fill in the statement, that's fine. You don't have, yeah, it is 0, answer 0. But the statement is the limit is 0 and the graph is continuous to the point 0, 0. Well, is 0 connected to this or that? It's actually the y. The 0 is the y coordinate of the point 0, 0. So the limit is connected to the y coordinate point. Let's go on to the next one. Okay, here's a graph. It says, what's the limit as x approaches 4? This graph has a hole at 4, 7. Try it on your own. Write the statement. I'm pressing pause. You press pause when you're done. Press unpause. Okay, let's see how you did. The answer is the limit is 7, and the graph has a hole at 4, 7. See the limit from the left, the limit as x approaches 4 from the left is 7, the limit as x approaches 4 from the right is 7. F of 4 is undefined. Function values are either defined or undefined. Limits are either exist or does not exist. So we say f of 4 is undefined, but the limit is 7, and the graph has a hole at 4, 7. If you want to use fancy language, if you want to talk like the textbooks communicate, you can say, the limit is 7, and the graph has a removable point of discontinuity at 4, 7, because a hole is a removable point of discontinuity. Just helping you with vocabulary there. Problem 5 is here. Try number 5 on your own. Pause when you're done, unpause. All right, let's see how you did on that one. The answer is the limit is 8, and the graph has a hole at 5, 8. Now, there's an item on the template on page 1 to cross off that we just never use it. And it's the one that says, number 8, cross off number 8. because we never talk about the point. We said, the limit is 8 and the graph as a whole at 5 comma 8 and a point at 5 comma negative 3. The 5 negative 3 has nothing to do with the limit, so we don't even mention it. All we say is that the limit is 8 and the graph as a whole at 5 comma 8. Next, try problem 6 on your own. You may begin. So the answer to this one is the limit does not exist and the graph has an endpoint at 3 comma 6. If this had been the limit as x approaches 3 from the right, then you would have said the limit is 6 and the graph has an endpoint at 3 comma 6. But this is a double-sided limit. The limit as x approaches 3 from the right is 6. The limit as x approaches 3 from the left, there's no train track. There's no place for the train to travel. It needs a track to travel. So the limit as x approaches 3 from the left does not exist. You can't say 6 does not equal does not exist. All you can say is that the limit does not exist. The graph has an endpoint at 3 comma 6. Try problem 7 on your own. Pause. On this one, you can say the limit does not exist. Whoops, a little farther down. The limit does not exist, and the graph has an even vertical asymptote at x equals 3. Some books, there's a little bit of disagreement in the mathematical community here. I know that's upsetting, but some books will let you say the limit is negative infinity, and the graph has an even vertical asymptote at x equals 3. I'm in the camp that says no, because if you're going to say the limit is negative infinity, then you're going to have to say something that should not be said, and that is that the left-hand limit is negative infinity, and the right-hand limit is negative infinity, and negative infinity is equal to negative infinity. No, it's a misuse of the equal sign to say that negative infinity is equal to negative infinity. So there are some calculus books. Larson stays away from that. Larson, our author, does not do that. But instead of negative infinity in this case, which is okay for a one-sided limit, but not a two-sided limit, say the limit does not exist and the graph has an even vertical asymptote at x equals 3. On the next page, try number 8 on your own. Pause. Here I hope you said the limit does not exist and the graph has a jump from 9 comma 3 to 9 comma 4. Or you could say, and the graph has a jump from 9 comma 4 to 9 comma 3. It doesn't matter what order those go in. Next, try number 9. And yeah, have fun with that one. Okay, this is, I think it's item 10 on the template, page 1 at the bottom. Here, we're looking at the limit as x approaches negative infinity. So the train is going here, the y coordinate, did I say, yeah, it's positive. As x approaches negative infinity, the y coordinate approaches positive infinity. So you can say the limit does not exist, or you can say the limit is infinity, either one. And the graph has a parabolic asymptote that opens up. Now, if this graph had a parabolic asymptote that opened down, we would have said the limit does not exist, or the limit is negative infinity, and the graph has a parabolic asymptote that opens down. Next, we're going to take the graph away from you. What if we have no more graph? It's just the limit as x approaches 8. Write down what you think this one is going to be. Pause. Alrighty. Number 1. The limit is 5 halves. How did I get that? I put an 8 in for x. 40 over 16 is 20 over 8. 10 over 4. 5 over 2 is 5 halves. So the limit is 5 halves, and the graph is continuous at 8 comma 5 halves. And you're expected to know that without taking the time to sketch the graph. In college algebra, yes, they taught you how to sketch graphs like this would have the degree of the numerator is 1, degree of the denominator is 1, so it's degree 1 over degree 1, the horizontal asymptote would be the horizontal asymptote y equals 5. There's a vertical asymptote of x equals negative 8 because the 0 of the denominator is negative 8. The y-intercept is found by pointing to 0, and for x you get 5/8 for the y-intercept. The x-intercept, wait, hold on, yeah. There's the x-intercept is found by putting a 0 in for y, and when you put a 0 in for y, 5x over x plus 8, That's equals 0. So wait, actually, yeah, the y-intercept is found by putting a 0 in for x. It's 0 over 8, which is 0. Yeah, that was a miscalculation on my point, because when the x-intercept is 0, the y-intercept is 0. So that means that the graph looks like this. But you're not expected to sketch the graph, x-axis, y-axis, because just by looking at this expression, you know there's a vertical asymptote at -8. Everywhere else, it's continuous. So all you have to do is put an 8 in for x and say the limit is 5/2, and there's nothing fancy going on at x equals 8, at x equals -8. If this had been the limit as x approaches -8, of 5x over x plus 8, then you would have been responsible for saying the limit does not exist and the graph has an odd vertical asymptote at x equals -8. But that's not the case. It's +8. Factor, and yeah, try number 2. I don't know what you're going to do with it. This will be interesting to see what you do with problem 2. Have at it. Okay, so this is probably pretty challenging for you. In order to make progress on number 2, you have to factor and cancel. Factor the numerator into x minus 4 times x plus 6. Look, there's a common factor. The numerator has a factor that's common to the denominator. So whenever factors cancel like that, that's a signal that the graph is going to have a hole, and the x-coordinate of the hole is going to be the 0 of the canceled factor. So the fact that the x minus 4 is canceled tells you that the x-coordinate of the hole is 4, and we're taking the limit as x approaches 4. To find the y-coordinate of the hole, you plug a 4 into the surviving expression. 4 plus 6 is 10. So based on this minor amount of algebra, we can tell that this graph, even though we don't take the time to sketch it, this graph is going to have a hole at 4, 10. And so the limit as x approaches 4, the limit is 10, and the graph has a hole at 4, 10. We know that without even taking the time to sketch the graph. Try number 3 on your own. Pause. All right, here we go. This is a limit at infinity. And when you have a rational function, then to evaluate a limit at infinity, you need to know whether the fraction as a whole is top-heavy, balanced, or bottom-heavy. Top-heavy is when the degree of the numerator is greater than the degree of the denominator. Balanced is when the degree of the numerator is equal to the degree of the denominator. And bottom-heavy is when the degree of the numerator is less than the degree of the denominator. When this is balanced, this is because it's degree 4 over degree 4. The only thing you have to pay attention to for the horizontal asymptote is that at infinity, the non-vertical asymptote will tell you what the limit is. So if you can find the equation of the horizontal asymptote, you've got the limit. And so when the degree of the numerator is equal to the degree of the denominator, you can find the horizontal asymptote by taking y equals the ratio of lead coefficients. 9 over 1 is 9. So we say the limit is 9, and the graph has a horizontal asymptote at y equals 9. There's a connection between the limit and some feature of the graph. The limit is the number in the equation of the horizontal asymptote. Try, next page, try number 4 on your own. Pause. So, this is top-heavy. It's degree 6 over degree 4. The degree of the numerator is 2 more than the degree of the denominator. If the degree of the numerator is 1 more than the degree of the denominator, then overall the function is linear. It will have a slant asymptote. When the degree of the numerator is 2 greater than the degree of the denominator, then the asymptote will be parabolic, opening either up or down. Since the ratio of lead coefficients, 9 over 1, is positive, this graph has a parabolic asymptote that opens up. If you don't believe it, type it into your graphing calculator, examine the graph, study the graph. We say the limit, this is as x approaches infinity. As x approaches infinity, the y-coordinate is approaching infinity, and the graph has a parabolic asymptote that opens up. Next, number 5. What's the limit as x approaches infinity of e to the negative x plus 5 over e to the negative x minus 2. Think about that one. Pause. All right, so what do we have here? We have the limit is negative 5/2. How do I know that? E to the x is one of the parent functions that you were expected to learn in college algebra. The graph of e to the x looks like this. And from your perspective, e to the x. I want to make sure that I'm doing this from your perspective. So e to the x looks like that from your perspective. And then e to the negative x would be a reflection over the y-axis. So e to the negative x, as x approaches infinity, e to the negative x is approaching 0. So think of this as 0 plus 5 over 0 minus 2. So it's approaching negative 5 halves. At infinity, we're talking about horizontal asymptotes. The limit is negative 5 halves, and the graph has a horizontal asymptote at y equals negative 5 halves. You can't just say, a lot of people make the mistake on the Unit 12 test of saying the graph has a horizontal asymptote at negative 5 halves. No, it's at y equals negative 5 halves, friends. And also, if you want to type this into your calculator in the y equals menu and you want to examine this, I would do parentheses. Here, in fact, I'll show you. If you're in classic mode instead of math print, you're getting close to being in calculus. So get out of math print and use parentheses in a thoughtful way. E to the negative x plus 5. This is how you would type it in. I'm going to put this down here so I can see it. In the y equals menu, I'm in parametric mode. We're going to learn about parametrics here in pre-calculus, but for now I'm going to go to function mode, y equals. Clear that we have some calculus notation in there that I'm going to delete. Okay. So I would type in parentheses. I can go the e to the x above natural log, e caret negative x, or I could just use this e over here with parentheses, plus 5, right parentheses, divided by left parentheses. Here, I'll do it the other way this time. I'll go second e caret parentheses negative x, close parentheses, minus 2. And close the parentheses there. On the viewing window, let's go from negative 100, no, let's go negative 20. Negative 20 to positive 20 by 5s. On the y-axis, we'll go negative 5 to 5. X res 3, okay. So, as you can see, when you trace this thing, as I trace over to the right, sure enough, there's a horizontal asymptote, the y-coordinate of the train. Here's a train going on the track. Train's traveling on the track. It's about negative 2.5. And it's getting closer and closer. That's the limit, negative 2.5. But you shouldn't have to look at the graph to figure it out. You should be able to get it without sketching the graph. Next, try number 6. Enjoy that one. Pause. Okay, so this is the piecewise function, but I'm not even going to take the time to sketch the graph of the piecewise function. I take the boundary value, put it into this rule. Every function has an input, a rule, and an output. And for inputs that are less than 7, the rule is input plus 5. So I know that one branch of the piecewise function has an endpoint at 7, 12, open circle at 7, 12. Another branch of the piecewise function has input this value. The rule for inputs greater than 7 is 2 times the input. So 7 goes in, you get 14. The limit does not exist in the graph as a jump from 7, 12 to 7, 14, or from 7, 14 to 7, 12. Now, that's where I'm going to wrap it up for today. So we'll come back. We'll get the rest of these on a different day dealing with limits. But here's the deal. I did not finish teaching you 6.1. So the homework that's due on, this is Wednesday, the homework due Thursday morning. Instead of assignment 5.7 and 6.1, just do assignment 5.7 and the problem set. So you don't have to do 6.1 for tomorrow. I'll adjust everything online so that you don't see the due date of 6.1. It just won't be there. So we're going to have to push hard. We have to fit Unit 6 into 2 days, into Thursday and Friday, but you know so much about the unit circle, we'll be able to breeze right through that. So I think you'll be in good shape. We'll be able to get Unit 6 in 2 days. So that concludes today's lesson. Your only homework is 5.7 and the Unit 5 problem sets. The Unit 5 test will be a take-home that you do on the honor system. You'll have to have it submitted by 8 a.m. on Friday. You are dismissed.